Hello, Internet. So, this challenge was yet another failure. This is the second failure that we've had in this series. It hurts. It's not satisfactory, but we learned a lot. We know exactly what the solution is, but Remix refuses to comply with our urges to win the challenge. Anywho, we shall continue in a calm and composed manner, Internet. Alright, so this challenge is called Gatekeeper 2. So this is the second of the Gatekeepers, and it's a similar challenge where you basically have to register yourself as an entrant to pass the level. Once you've done that, you're all groovy and you succeed and get past the challenge. You can see that listed here. Now, the next piece is giving you some tips on things that might be useful to understand or comprehend for this. So the first and foremost, it basically asks you to remember what you've learned from the first Gatekeeper. So that's kind of a sign that we're going to use some of the stuff that we used from the first session here. Next part is talking about assembly and the keyword of assembly and what that really means and what it kind of entails. In addition to that, it talks about a specific piece of assembly that we're going to use here, which is called ext code size, which is exact code size. And it's basically going to check to see the size of a contract's code. It's going to check the size of that when it kind of pings off to an address. Additionally, it's calling out this character here with, and within Solidity, that's basically referring to XOR operators, and you can give that hint there. And all of these come with links. So they link out to the yellow paper, which is kind of like Greek and hard to understand. Then there's basically the documentation that links you out to this specific opcode to explain exactly what they've explained here already. And then there's a link here that basically talks you through the XOR operator, which I think goes out to the documentation. Those are our links, and we can quickly click through these to show you what's inside. So this, like I said, is referring to assembly, and you can see it talks about inline assembly, what that is, and then it talks about examples of what inline assembly look like. And then if you just go in here and type in control find for exact code size, you'll see that in this table it refers to that and basically states that it's showing you the size of the code at the address that you're pinging to. Yellow paper talks about this as well, but like I said, it's convoluted and not very understandable. I think the only thing in here that was useful is possibly this note here. I'm going to have to reread it to see if it was something I used. Alright, so this is partially useful. The only reason it's useful to me now is because I've read multiple explanations of what this is referring to. I don't think this is the most suitable way of explaining this, but this piece here inside of the yellow paper is somewhat insightful if you decided to read it. But we're not going to explain that point through this because there are better explanations, or at least more comprehensible explanations. Okie dokie. So first things first, disappointing, disappointed, but we learned. Remember, darn you. We couldn't get satisfaction of actually executing this correctly, but with that being stated, we still learned a lot. And the interesting thing is I used multiple solutions, and none of those worked within Remix for me. So I partially blame Remix, even though it's probably a stupid human error that I'm making. With that being stated, if you, past April 4th, 2022, have solved the solution via Remix, you should totally hit me up in the comments and let me know specifically what you did, or if you know the error that's occurring, because I'll show you the error that's occurring for me. And I'm going to show you the error, and if you know what the error is and you know how to solve it, let me know. Hit me up in the comments, and not in the DMs. Hit me in the comments in YouTube, because I don't have DMs for you to DM me. Comments on YouTube, let me know, and that will make me feel better, because I can get the satisfaction of actually solving this challenge, or at least knowing what I was doing wrong. With that being stated, let's walk through the solution, the target, and all that stuff. So as per usual, we have our target code here, our attack code here, we have our notes here, and I think what I'm going to do is I'm going to walk through the code first for the target, just so we can understand what's going on. And I'm going to copy this down here, remove all the comments so it's not as overwhelming. And then I'll talk through my comments later on. But first I want to give you kind of an intuitive understanding of what's happening with the target code before we jump into all the nitty-gritty details. Okay, we'll start here. Now, with this challenge, first things first is, per usual, we're setting up our compiler version, which is 6.0, but this is going to be 8.0 for Remix when we run it, and we're going to change this, keep it as a floating point, but remember this is bad practice. When you do things in production, this should be static. contract is called Gatekeeper 2. We're setting a state variable here, which is entrant. And that entrant, when you run this inside of your console for the challenge, it's going to pull back all zeros. Reason being is that's correlating to false. And we have a few modifiers. So this is similar to Gatekeeper 1, where we had our 3 trolls that we had to get past to get to the gold. And we have our 3 trolls here. So we have troll 1, troll 2, and troll 3. Now this first one is it's identical to Gatekeeper 1. So we're going to use we copy and paste the solution from Gatekeeper 1 to here. And this is pulling from what we learned in telephone. And really what we're going to do for this is we're going to utilize our contract to talk to this contract to ensure that we can pass this requirement. The requirement basically states that we want to ensure that the sender is not equal to the origin. And by running this through our smart contract and then bringing it back into here, it's going to allow us to pass this because we're not acting as the sender. We're acting as the origin. All right. The second one here is referring to the assembly code that we've talked about briefly. So this is pulling out that code here. So here we have a state variable, a local variable inside of this modifier. And this is basically setting it to x. So x is a uint. We're going to have our inline assembly, which is what's happening here with these brackets and this calling of the word assembly. We're going to then basically associate the value derived from here to x, and we want to ensure that x equals 0. So the value derived from here is basically saying that the caller of this contract, which is going to be us, when we call this contract, it's going to check to see what the size of our contract's code is. And if our contract's code is more than 0 or not equal to 0, then it's going to fail. It's not going to allow you to pass. So our intent here is we need to ensure that our contract code size is 0 when we call this contract. We'll walk through specifically how to do that in a second. So that's that piece. The next piece is gate 3, which is basically taking our key similar to Gatekeeper 1. So we're going to put in our key, which is bytes 8, which is also uint 64. It's the same thing. So 64 bits, 8 bytes. And then the requirement here is utilizing this symbol here. Oops, which is redo. Yeah. The symbol here, which is XOR. So that's going to be XOR bitwise operation that we're going to do between these two values here. So this value here is going to be basically our sender address. It's going to be encoded and packed. It's going to be hashed. Then it's going to be put into bytes 8, which is then into uint 64, which is the same thing, but I guess they wanted to do that to make themselves feel better, or there's maybe a reason for it. And then we're going to XOR that against our key, which is going to be uint 64, which is the same thing as bytes 8. Once we've XORed these together, then they're going to have to equal the value derived from this, which is uint 64 0 minus 1. And in my notes, I explain what this is, and we can jump to that in a second. But in a nutshell, it's basically going to end up being all ones across the board. All right, so once we pass this, we go to our function. This is where all the magic happens. Now, let me bring this up here. Oops. Turn that off. Okay. So down here, we can see that we have our function. And the function is called enter, so the same as Gatekeeper 1. We're going to input our key, and then our key basically has to pass every single one of these trolls. Once it passes all the trolls, then it will return a boolean. And that boolean should be true. And once it returns it, it's going to assign our address, our origin address, to the entrant, and it's going to allow us to be labeled as the entrant, which is going to be up as a state variable that's set. It's going to return true, and that's going to allow us to basically pass this challenge. So that is, in a nutshell, at a high level, what's happening with this target code here. Now, I think we've talked through most of what my notes say here, but let me double check. All right, yeah, so I think the best way to approach this is now we're going to talk through specifically gate 2 and gate 3, but I'm going to talk through it via my notes because there's some interesting graphs and links in here that'll help. So for gate 1 is per usual, so we're just going to use the same exact code we used for Gatekeeper 1, we're going to use for gate 1. And Gatekeeper 2 is referring to the exact code's assembly. So the first link that is useful, that kind of gives you insight to what's going on, is this blog here that basically it talks right to the root of what we're going to do. And you can see it in the title, we're going to bypass the Solidity contract size check. So the size check they're going to do on us, we're going to bypass that. And there's a graph here that really walks you through that in a high level. So this example 1 is basically how it would work if we didn't modify our contract and do some malicious stuff, where you basically try to run your smart contract And let me take a step back. So the reason they're doing a check size or checking the size of the contract that interacts with them is they want to basically ensure that the only thing that can access their contract is a human and not a smart contract. And that's going to be an externally owned account instead of a smart contract. So this wouldn't work because this has some sort of size. But if you interact with an EOA or an externally owned account, aka a human, that code size should be 0. And that basically sets up an access control to say, I don't want anything to interact with my smart contract unless it's a human. And that's when they do the check of the size of the code. But as a malicious user, what you can do is you can actually, within your smart contract, if you input a function in the constructor, so you can see that mentioned here, if you input a function in your constructor, and that function is called within the constructor prior to the code actually being established and initialized on contract, the code size will actually be 0. So when I call this to check the size of the code, and the contract is being deployed, and when that contract is deployed, and it's using the constructor, we'll say con here, and inside of that constructor there's a function, and that function actually calls this contract, then when this does the check, it's going to initially be 0 because the code hasn't been deployed and initialized, so there is no code to be measured. There is no size to be associated. And that's kind of the simplistic understanding of what we're doing here. And if you actually go back to our notes here, you'll see it kind of mentioned all that stuff here. Another resource that'll be useful is to show you kind of what inline assembly is and just walks you through specifically how that works. In addition to that, another section is the example code for a video, a YouTuber that we talk about quite often, which is the smart contract programmer, I think. Yeah, so he did a video here basically walking you through .7 hacks, but this applies to this challenge. And basically he talks about how you can avoid the code size. And the example code's here. So you can use this for your hack. If you, not this specific code, but this will give you an intuitive understanding of what's happening. In addition to that, OpenZeppelin actually has a specific modifier that they use for certain circumstances, and people can actually import this into their contracts and use this this kind of modifier. And the modifier is called isContract. So it's checking to see if it's a contract or not, and it's checking the length, similar to what we've already discussed. But instead of using the assembly, it's going to use this check here, basically saying account code length over 0. Now the interesting bit about all this stuff is if you look at the top here, you'll see there's tons and tons of disclaimers saying that you should not use this specific modifier for checking to see if it's a smart contract, even though it's called smart contract, or not to check, but I guess to check in the sense of it being an access control. So anytime you use access controls, you need to ensure that there's minimal or no ways to maliciously kind of prevent that, or at least don't allow this to be your only form of access control. There should be multiple levels, defense in depth, the whole concept. But in here you can see in the notes, they basically state multiple times that it's unsafe to assume that an address for which this function returns false is an externally unknown account and not a contract. If it returns false, aka means that they're assuming that it's an EOA, but it's not. Another interesting thing here is they basically list out the items saying that, among others, isContract will return false for the following types of addresses. If it's an externally owned account, if it's a contract in construction, if it's an address where a contract will be created, or a contract that lived but's being destroyed. Now this one here is what we're going to leverage. We're basically going to incorporate our function into our constructor, so as our contract is constructed and it's calling the other contract, it'll still be 0 until it's completely deployed. So that's interesting to see kind of how they've called this out multiple times, because it has been a recurring issue within the sphere of the Ethereum universe. And that was that. Cool. So that is that for solving gate 2. For gate 3 specifically, what we're going to do is we're going to talk about the XOR piece, because the XOR piece is what we need to kind of manipulate and modify so we can pass that third troll. So I have a link here that brings you right into Wikipedia, and Wikipedia I think does the best job at explaining specifically what bitwise XOR operations are for binary. And I'm not going to read all the text, but you can get an intuitive understanding of what's happening here by just looking at specifically the examples that they provided. And in a nutshell, I've actually have a short sentence in here that I felt really synthesizes best. So an XOR bitwise operation, so when comparing binary digits, so ones and zeros, if any one differs then it equals 1. So if anything differs between the two, then it's automatically going to default to 1. If any of these are the same, it's automatically going to default to 0. And we can see that manifest in this example here, where you have your 0s, 1s, 0s. So this is going to be, remember, this is going to be our value. This is going to be the kind of the mask, but not really. So this is just the comparison. And this is going to be our output. So we have two things that match. So that's going to be 0. We have two things that are different. That's going to be 1. We have two things that are different. That's going to be 1. We have two things that are the same. That's going to be 0. And that's kind of how the XOR operation works here for binary. There's many reasons why this is used within computer science generally. And if you're interested in Wikipedia, they actually have a write-up. I thought they did. Maybe I lied. Applications, yeah. So in applications, they kind of walk you through the use for this type of stuff. So you should definitely check that out if you're interested. This map kind of just gives you another intuitive understanding of what this looks like for the different types of operations on binary. So and both things need to be equal. XOR, either or has to be different. And then or is basically either or has to be the same. Now, the key part of utilizing XOR and the thing that we're going to leverage to understand how to solve this challenge is that with XOR operations, you can swap the variables. And here I have a simple kind of formula to show you what that looks like. So up here, you can see that we have AB equals C, and then B equals A. So if you do XOR A with B, you'll get C. And if you XOR B with C, you'll get A. And that's kind of how XOR operations work. And we can apply that to the example here, or the example we walked through in Wikipedia, but we'll just do it here just for simplistic reasons. So this might be somewhat faded because it was inside of a video that I've linked somewhere here. I've linked the video. And in this explanation, it's basically showing you here are the binary digits that we've combined with this initial. So this is going to be, let's say this is A, we'll say this is B, and we'll say this is C. And then what we're going to do is we're going to take A once more and combine it with C to get B. Or this equals this. Yeah, okay. So we did 0 and 0 equals 0. We did 1 and 1 equals 0. 1 and 0 equals 1. So different, 1, same, 0. Different, 1, same, 0. Same, 0. So that's what we're going to get here. So if we take this and take A and bring it down here and apply it against C, we're going to get B. So if you do same equals 0, we'll do different equals 1. Different, same equals 0. Different equals 1. Same equals 0. You can see all this stuff is, if we combine these two, we're just going to get what we had here in B. The reason this is relevant is if we go to our code here and we look specifically at the gate 3, we can see the requirement here is basically saying that we need to take this item here, we need to XOR it with this item to then get this item. Well, the thing is, the only thing that we do have at the moment is we have this item here because we are the sender, so we automatically get this value. We don't really necessarily know the key yet, but we have this formula. So if we basically take this, and we're going to take, say this is C, this is B, and this is A, what we're going to do is we're going to take A, we're going to XOR A with C to then get the key. And once we have the key, then we can run that through our challenge down here, and we can pass all the gates and get up past all the trolls. And that's basically what we're going to do here. Is we're going to swap those things around to get the key. So with that being stated, that's the intuitive explanation there. Another link that I'll walk you out through is this one here. So this is the 2018 one, so it's slightly outdated. But as per usual, they do a great job explaining a lot of what's discussed in the challenge and really breaking things down. This is a simplistic snippet of the attack that we can actually utilize to kind of show you what's going to happen. And I'll just show you that inside of VS Code. But with that being stated, those are the notes. Those are the gates and the trolls. This is the attack. So if we look at this, we can see that we have the pragma set up. So per usual, same thing. We have our contract called let me in. And then here we have the constructor. Now see that we have no functions, right? There's no functions down here. It's just a constructor. Reason being is we need to pass gate 2, right? So if we deploy our contract and we only have a constructor and we're calling the enter function inside of here, then that's going to allow us to have our code size is equal to 0. Additionally, we're going to pass gate 1. So this is gate 2, which is going to allow our code size to be 0. Gate 1, we're calling this a target address through another smart contract, which is going to help us pass gate 1 because we're going to avoid being the origin sender. And then gate 3 is where all this comes into play. And really, remember how I told you just need to swap the things out? So remember, this is going to be A, and this originally was C because we've actually swapped this out for B. And then when we XOR these together here, that means that we're going to then get B, which is going to be our key, right? And then here we're just going to catch that value and put it in key. Once we've caught this value, we're going to run the same exact thing we ran in gate 1, which is we're going to input our key here. We're going to encode the function that we want to call with the bytes 8 piece. So we can combine these together. And when we do that, we're going to run it through a call. We're going to call it on the target address here. Once we've done that, and theoretically, we would have solved the challenge. We would have been done. We would have been super excited. We did the challenge, everybody's happy. But I continuously keep getting errors. And I'm going to show you exactly what errors I'm getting, just so you can hopefully give me the answer in the comments. All right, so there's a target address. If we were going to run this, we would do inject web3, and this is our attack contract. So let's save that so it exists. So call attack, we'll apply that to the address we want to target, we'll deploy it. This gives me an error, and I've Googled this. I've looked at every single link on the first like 3 pages of Google and DuckDuckGo, and I've not found an answer to how to get past this piece here. If I add some way, I get another problem, and that's something I've Googled and I can't get the answer to it. So internet, if you know how to get past that problem and actually get this to deploy and do what we want it to, that'd be great. But if not, that's the challenge, and that is going to be Gatekeeper 2. I'm going to move on to Notcoin because I don't want to waste any more time Googling and trying to solve this simplistic error, even though it's really complex for me apparently because I can't solve it. Anyway, we learned a lot. We understand about XORs. We understand about the exact code size for contracts and different types of assembly that's in line with the contract and all that good jazz. That being stated, I will see you on level 15, which is Notcoin.